Rose Chiginto from PSECE 5A, and I am here to present to you my microwave link design. Microwave link design. First, let's have a little introduction about microwave. Microwaves are electromagnetic waves with frequencies that range from approximately 500 MHz to 300 GHz or more. The prefix micro in microwave is not meant to suggest a wavelength in the micrometers range. It only indicates that microwaves are small compared to waves used in typical radio broadcasting, falling along 1.0 mm to 30 cm, which are slightly longer than infrared energy. Here are some applications of microwave. Studio to transmitter links for radio and television broadcasting, head ends to distribution system of many cable TV, point-to-point links as a backbone or tails of large networks for private and government entities, point-to-multipoint system for TV, telephony and data, air traffic control center interconnectivity, short-haul applications such as linking offices and buildings in congested urban areas, and lastly, military applications. In broadcasting, they used microwave links to send programs from the studio to the transmitter location, which might be miles away. Microwave links carry cellular telephone calls between cell sites. Wireless internet service providers use microwave links to provide their clients with high-speed internet access without the need for cable connections. Telephone companies transmit calls between switching centers over microwave links, although fairly recently they have been largely supplemented by fiber optic cables. Companies and government agencies use microwave to provide communications networks between nearby facilities within an organization, such as a company with several buildings within a city. And next, here are the initial steps involved in microwave link design. First, site survey or selection. Site ocular, which includes weather, wind velocity, soil pressure, access roads, and aerial photograph. Next, it's path profiling. It needs topographical map to read contour lines and determine elevation between two sites, such as type of terrain, earth bulge, K factor, or canal zones. Then, link budget calculation. It involves equipment parameters, frequency selection and assignment, appropriate radio equipment to determine required transmitter power and threshold power. Site survey or selection. Site selection is the process of choosing the optimal location for an anticipated use. It involves measuring the needs of a new project against the merits of potential locations. Since microwave communication is a line of sight communication, the first step in choosing the location of the transmitter and receiver sites is verifying that there are no natural and man-made obstructions between them. In cases where a straight path with no obstructions is unavailable, a repeater can be employed to relay signals over the obstructions so that the signal can cover longer distances. Next is path profiling. A path profile provides information on where interference may occur and aids in selecting an appropriate path and antenna height. Microwave signals are affected by conditions of possible obstructions, reflections, atmospheric conditions, and the curvature of the Earth. The curvature of the Earth or Earth bulge should be considered in planning a microwave system. First thing to solve in path profiling, Earth bulge. Earth bulge is a term used in telecommunications meaning the curvature of the Earth's surface, which limits the range of communication methods that require a line-of-sight path, like high-frequency radio waves, microwaves, or lasers. Here is the general equation of the Earth patch. Ht is equal to d1 times d2 all over 12.5 times k. Next is the path clearance equation. H equals to H1 equals to H minus HO plus d1 over d times H2 minus 1, wherein H equals to path clearance, HO equals to total height EB plus E plus tree growth, H1 equals to earth elevation plus tower height at site 1, H2 equals to earth elevation plus tower height at site 2, D1 equals to distance from site 1 to HO, and D equals to total distance. And then line of sight. Line of sight is a type of propagation that can transmit and receive data only where transmit and receive stations are in view of each other without any sort of an obstacle between them. FM radio, microwave, and satellite transmission are examples of line of sight communication. So here is our line of sight formula. Loss equals to H plus HO, clearance from first Fresnel. C first equals to loss minus HN plus HO, wherein HN equals to Fn, the end Fresnel zone radius. And lastly, that we will compute for path profiling is the Fresnel zone. Fresnel zones are a series of concentric ellipsoids that surround the path from the transmitter to the receiver. The first Fresnel zone is the surface containing every point for which the sum of the distances from that point is exactly 1/2 wavelength longer than the direct path. Fresnel zone radii are radii of the concentric circles corresponding to the cross-section of a particular Fresnel zone. So here are the formula for our Fresnel zone. First Fresnel zone radius F1 equals 17.3 square root of D1 times D2 all over F times D. The end Fresnel zone radius Fn equals to F1 square root of N. Fresnel zone clearance Fc equals to 0.6 times F1. So through Excel, we can easily compute for the path profile natin. Ito ating D1 is actually hanggang 29 kilometers yan. Kaso hindi kasya sa ating PowerPoint, kaya hanggang 10 lang yung nilagay ko. Ganun the same with the distance to natin. Pero ayan nga, pag nilagay na natin yung automatic naman sa Excel na pag nilagay mo yung formula, makukompute mo yung mga kailangan mo. Ayan, makikita naman natin dyan na maliliit lang, halos point lang yung pinagkakaiba ng mga sagot natin from Fresnel zone high, low, Fresnel clearance high. Ayan, puro point lang yung kanilang pinagkakaiba. Kaya tingnan nyo ang ating graph. As in, straight line lang siya. Halos parang nagpatong-patong yung ating Fresnel zone, ang ating mga Fresnel clearance. Kasi ang ating y-axis, ang ating elevation ay masyado mataas. Itong distance ng ating y-axis, ayan. So, by 3D, makikita natin na halos pantay-pantay lang yung ating mga Fresnel zone and line of sight natin. Kasi nakita naman natin sa data natin kanina na puro point lang yung kanilang pinagkaiba. So, next, sa ating link design na kailangan, link budget. A link budget is an accounting of all of the power gains and losses that a communication signal experience in a telecommunication system, from a transmitter to a medium, free space cable, waveguide, wave fiber, etc. to the receiver. So here, ito yung mga design specifications na ating kakailanganin. Ang ating site A, which is ang ating transmitter, mataas na bundok, ating location. Site B, which is ang ating receiver, Mount Banoy, and then total distance from site A to site B ay 29 kilometers. So, ito yung ating mga materials na specifications. And next is ito, makikita natin yung ating mga datasheet. By search lang natin to kung anumang Google, ganyan, search natin, makikita na natin yung datasheet at pwede natin i-download. So, ayan. Transmitter and receiver radio is the DAR12HB radio. Ayan, nakalagay naman yung kanyang frequency range, 10.5 to 13.2 GHz. Ang ating transmitter output power, receiver noise figure, receiver threshold, system gain, typical signal to noise. Next is ang ating transmitter and receiver waveguide, which is RFSE 105J. So, ayan, 10.5 GHz ay 2.83 per 100 feet. Next is transmitter and receiver antenna, which is yung kinuha nating antenna, radio waves SP3-10. Ayan, kanyang specifications. Next, meron na tayong mga gamit, meron na tayong mga data na kailangan natin sa datasheet. Nakuha na natin siya. So, pwede na natin computein yung ating link budget. So, link budget calculation natin. Ayan. Transmitter radio power output, PO equals to 33 dBm. Transmitter waveguide loss, attenuation over length times total length. Ating total length ay ang ating tower height plus antenna height. Ayan, LTX equals 0.97 dB. Next is, ayun, nakalagay naman sa data natin kanina, transmitter antenna gain natin ay 36.9 dBi. Effective radiated power, EIRP equals to PO plus GTX minus LTX. Ang naging sagot natin ay 68.93 dBm. EIRP or effective isotropic radiated power. Ito yung power na nararadiate o yung power output ng transmitter antenna natin. Ibig sabihin, ito yung dadaan sa ating free space loss or path attenuation. FSL is the loss that would be obtained between two isotropic antennas in free space where there are no ground influences or obstructions. It is also defined as a loss incurred by an electromagnetic wave in a straight line through a vacuum with no obstruction or reflection of energy from nearby objects. Yan ang ating free space loss computation. FSL equals to 92.4 plus 20 log F plus 20 log T. By the way, ang ginamit kong frequency dito ay 10.5 GHz. So, substitute lang natin yan. Makuha natin sagot is 142.07 dB. So, ang ating isotopic receive level, which is yung power level na dadating doon sa ating receiver antenna, ay yan. EIRL equals to EIRP minus FSL. 68.93 dBm minus 142.07 dBm equals to negative 73.14 dBm. Next ay ang ating link budget calculation. Nasa may part na nga tayo ng nakatawid na tayo sa FSL. Ibig sabihin, nandun na tayo sa part ng receiver side natin. So, receiver waveguide loss, attenuation over length times total length. Ganun ulit. Receiver antenna gain natin, 36.9 dBi. Receive signal level, ito yung power level na makakarating dun sa mismong receiver talaga natin. RSL equals to IRL plus GRX minus LRX, which is ang nakuha natin negative 37.21 dBm. And next naman ay ang ating fade margin. Fade margin or FM. It is the fudge factor included in the system gain equation that considers the non-ideal and less predictable characteristics of radio wave propagation, such as multipath propagation and tearing sensitivity. It is an attenuation allowance so that anticipated fading will still keep the signal above specified minimum RF input. So, ito yung ating computation ng fade margin. Meron tayong receiver radio threshold na negative 84 dB. So, FM equals to RSL minus RX threshold is equal to 46.79 dBm. So, lastly, sa ating link budget propagation reliability, so meron tayong relay table. Yan. So, ayan. Diba, nakuha nga natin na FM ay 46.79. So, gamit yung ating relay table, makukompute natin yung ating propagation reliability, which is i-ship solve lang yan, lalabas na yan, R equals to 99.998%. Ibig sabihin, ang ating link design is possible na magawa. So,
that's all for my presentation. Thank you for watching.